So varactor diode is nothing but a device, a PN junction device, which offers a variable capacitor. So that's the symbol of a varactor diode. You can see the symbol of a diode, and we have two horizontal lines indicating capacitive nature of the device, and we often put an arrow on this further indicating the variable capacitance nature of the device. So there is something called as biasing of the varactor diode. Now, how do you bias the varactor diode? We can use simple potential divider circuit. So let's say we apply some positive voltage to a series connection of two resistors R1 and R2. In that case, at the midpoint, we will generate some positive voltage, which is given as R2 upon R1 plus R2 into V plus. I can simply connect a varactor diode across R2 by having its cathode side connected to the midpoint and anode going to the ground. So basically you can take varactor diode as a normal PN junction diode, which is operating in reverse biased mode. So in reverse biased mode, we all know that any PN junction diode can act as a capacitor, because there's a depletion region formed between two conducting regions of N-type and P-type. So that capacitive effect is something we are using in the form of a varactor diode. So varactor diode right now is biased to act as a capacitor, and right now you can see everything is fixed. The positive voltage level is fixed, R1, R2 values are fixed, so the varactor diode will offer a fixed capacitance, which we have already mentioned to be CD. So if I draw the characteristics of varactor diode, in which we will show the capacitance CD as per the voltage that appears across varactor diode, I'll call it VD. So let's say if we mark this voltage as VD, in that case, right now voltage VD is some constant value, and that gives me some constant value of the capacitance. So this is that point which you can call the biasing point of the varactor diode currently. Now what is going to happen, we will apply the input signal in the form of m of t. So m of t, which is my modulating signal, will be given at the interconnection of the two resistors. So what is happening now is, if you calculate the overall voltage across R2 in the form of VD, it is going to be a constant DC voltage, which is R2 upon R1 plus R2 into V plus, which will keep varactor diode biased at a specific point, making it offer capacitance of CD. And now you will apply AC voltage m of t. M of t will be, if it is a single sinusoidal signal, as per our assumption, it will be single AC signal. In practice, it will be a time varying signal, but its amplitude will constantly keep on changing. So as m of t amplitude changes, the voltage VD will also change, but it will change around this fixed value that we had previously. So around this fixed value, the voltage will keep on changing, and as the voltage keeps on changing, the value of the capacitance offered by varactor diode will also keep on changing. So please remember that if you increase the value of the voltage across the varactor diode, that means if you make it more and more reverse biased, then the depletion region width will also increase. If the distance between the two conducting plates in a parallel plate capacitor increases, we know that its capacitance will decrease. So if you increase the reverse biased voltage, the capacitance will decrease, and if the reverse biased voltage is at its minimum, then the capacitance will be maximum. So if I draw the characteristic, it will look something like this. So you can see I can obtain a capacitance between two different value. So this is the range over which the capacitance will change, and for this, to obtain this, I'll have to vary the m of t also over a range from minimum voltage to maximum voltage. So as we vary the signal, input signal m of t, as m of t changes, the voltage will also change around this constant DC value, and as the voltage changes, you can see we will obtain a variable capacitance.